To go through an example of second order dynamics, what I'm going to do is take a look at this given second order process that will have numerator dynamics and go through how we can determine what the output in the time domain due to a unit step input will look like. And so what I mean by that is if we go back to the definition of our transfer functions, we know that they map the response of an output to an input like u of s. We know that a unit step input u of s will have the form 1 over s, so we can ignore it. But what we're going to do is take a look at this equation here and begin to evaluate what our zeta is, our damping factor, as well as what our time constants are. And so to do that, we're going to divide all the terms by 36, like so. We're going to realize that g of s is really equal to 1 times s plus 1 over 6 quantity squared, 1 over 36, times s squared plus 36 over 36, which is equal to 1 times s plus 1. And if we look further, what we'll realize here, based on what we know about second order transfer functions, they have the generic form tau as plus 1 over tau squared s squared plus 2 zeta tau s plus 1. We can see that tau must be equal to 1/6. We can also see that 2 times zeta times tau is equal to 1, which is equal to 2 over 6 times zeta. And therefore zeta must equal 6 over 2, which is greater than 1. And because we know that zeta is greater than 1, it means we will have no oscillations because it's overdamped. And finally, what we see is that tau a is equal to 1. And because of that, it's greater than tau, which was equal to 1/6. Therefore, we will observe overshoot. And so what this means is that what all of this information tells us is that in the time domain, if we wanted to look at how our output y will respond to a step input, a unit step input, what we would find is that we would have an initial response, and then it would return back to the new steady state value. And it is also important to note we have no oscillations, but we do observe overshoot. And this is the key takeaway from the data that we learned here. And this wraps up how we can be able to go from the frequency domain and with a unit step input approximate and model what we expect the behavior to look like in the time domain based on what values we obtained for zeta, what we obtained for the numerator time constant as well as the overall time constant, and how we're able to get these graphs at the end of the day. So it does help us visualize how our output will respond, and I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.